All right, today we are kind of doing our first real lesson in Unit 3, working with exponential functions. And we're going to do this over the course of a few days. Here's our objective, being able to describe and evaluate exponential functions. So keeping our actions like very simple and just kind of grounding ourselves in what exponential functions are. So we did a couple of activities in class to kind of explore this idea. But let's start taking notes here and getting down a definition. Hey, what is an exponential function? And basically, it's going to be a function that includes the input in the exponent. The general form it's going to take is this: there's some number raised to an exponent, and that exponent is going to include x. Now, we might have it be something like 2 to the, oh, sorry, I got the wrong thing here. We might have it be 2 to the x. We might have it be some decimal to the x. Maybe there's something going on with the x. Oftentimes we'll see like a problem where we multiply a big number times some decimal to the x minus 1. There's going to be a variety of formats we're going to see, but basically our input is going to go into the exponent when we have an exponential function. Now, there's two main types that we're going to see and we're going to work with. The first one is growth, and this is going to happen when that base number, if I go back to my general form here, when that b to the x, when that b value is greater than 1, we are going to see growth. Our graph is going to start kind of low and go up exponentially over time. And if we have a base number that's in between 0 and 1, then our graph is going to start high and decay over time. Now, if we think about what's happening towards the end of these graphs, the exponential growth comes from the idea that, man, we are just going to go up, 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 and up in almost a straight line as we continue going. Whereas decay is it's going to kind of approach 0, never quite hit it as it continues on to the right. Now, focusing in on that base number is going to be a big thing today. So I want you to kind of input and see the different Desmos graphs for these two functions here. For example, 1, we have a base number that's greater than 1 with 2, so we're going to expect growth. And for the second one, we have a base number that's less than 1 with 0.5, so we're going to expect decay. Let's just type those in, see what's up. F of x equals 2 to the x power, and we can see, yeah, that's exactly what we expect, right? We expect a graph that is kind of starting at 0, coming up, hits our y-intercept, and increases exponentially. If I type in my other function, f of x equals 0.5 to the x power, and I'll turn off my red one. Okay, here's an example of decay where we actually start high and kind of go that other direction where we flip and kind of start approaching 0 as our graph continues. So, just like some of our other functions, we can have some simple transformations just by modifying our base equation. So I want to point out that this equation here, which you should get in your notes, still kind of is built around this idea of b to the x power. However, we have these different coefficients out in front. Our a coefficient is going to be kind of our vertical stretch or compression. Our C coefficient is going to move our graph either left if it's positive or right if it's negative. Remember that horizontal shift is kind of the counterintuitive directions. And then D is going to shift our graph either up if it's positive or down if it's negative. So just like before, I want you to take a look at, well, first off, make sure to have this form written down in your notes. But I just kind of want us to play around, see what the different shapes look like. Notice how in all of these equations we have a base of 2, but we're doing different things to them based on those different coefficients. And I just kind of want you to see how that graph changes. So if I go to example 5, I go in and type in, I got my f of x equals 3 times 2 to the x. Okay, and if I compare that to what my 2 to the x was, all right, notice how the graph kind of takes a slightly slimmer shape to it. If I change that to a 1/3, now my graph kind of takes a wider shape to it. If I move on to example 7 and 8, where we're playing around with that exponent value up top, okay, this one can be a little tricky to do in Desmos. So I recommend almost throwing parentheses up there to ensure that it gets typed in. But we have x plus 3, which kind of moved our graph. If we look again, it moved it to the left 3 spots. We have x minus 3, which moved our graph to the right 3 spots compared to our original. And lastly, looking at the up and down shift with 9 and 10, notice how this value of 3, this coefficient, isn't grouped up with our exponent, right? It dropped lower. So we just got to be mindful of how we type that in. If I add 3, it just moved my graph up 3 spots. If I subtract 3, it moves my graph down 3 spots. All right. Now we've just kind of generally talked about the general idea of exponential functions, the shape of the graph, etc. We're going to identify some key features again tomorrow to help us do some modeling. But today, one of the things I want to focus on is this idea of growth versus decay, and being able to recognize both from the graph and from the equation whether or not something is growing or decaying. And we want to focus on that b coefficient, which is our base of the exponent to make that decision. So if I look at example 11 and I look at 3 here, remember back to our rules up in our notes earlier, if b is greater than 1, then we have growth, whereas decay, it has to be 0 less than b is less than 1. So I look here and I see that, hey, my 3 is greater than 1. I'm just going to put a little note. This is greater than 1. So that means in example 11, we would have growth. And if we graphed this, we could easily see this as well. F of x equals 3 to the x. So if you're ever stuck, throw it in Desmos. Ensure that you're getting a growth graph. And then if we look at example 12, okay, we have 0.95 as our b, which is in between 0 and 1. And so this is going to be a decay graph. Again, I can check that in Desmos to kind of just see what's going on, confirm that that's good, 0.95 to the x. And it's slimmer, but we definitely are, if I zoom out, decaying over time. Example 13 and 14, there's some more numbers going on. We're multiplying by stuff. But again, focusing on that base number of 5. And then example 14, that base number of 1/4 is going to drive what we have. So for example 13, we're expecting growth from that because that base number is greater than 1. Example 14, we're expecting decay because we are in between 0 and 1 for that graph. All right, the last thing that we're going to do today is work on just evaluating these exponential functions. It's a foundational skill that's going to come into play the next few days. So we got 4 different examples here. For each of these, we're going to basically plug in our input and evaluate it. So in example 15, we have f of x equals 2 to the x when x equals 3. So really what I want to do is plug in f of 3 equals 2 to the third power. We write everything exactly the same and just replace that x with 3. And if we evaluate that out, 2 to the third power is 2 times 2 times 2, which should give us 8. That's our answer. Let me just show you a couple quick ways you can do this with Desmos as well. First off, if you take this 2 to the third power and just type it in, 2 to the third power. Desmos acts as a calculator. Notice how it gave us the answer 8 here. Really easy way to just make sure that you're doing your evaluation properly. And that other way we've learned before, if I type in my function f of x equals 2 to the x, and then use another line and type in f of 3, then this second line tells me what that value is as well. Okay, so there's 2 ways to do it. For the sake of today, it's probably easiest and quickest to do it like I did in row 1. But just remember that there's a couple ways we can use Desmos to help us evaluate. Now, this next problem, f of x equals 5 times 2 to the x when x equals 4. So I'm going to kind of plug in my 4 now for this case. F of 4 equals 5 times 2 to the 4th power. And if we think of our PEMDAS up here, we want to do our exponent before we do multiplication. So this is always going to come into play as you do this. So if you do try to do it manually, you would get 5 times, and 2 to the 4th would be 16. And then you would get 5 times 16 gives you 80. However, this is where if we utilize Desmos and just type in 5 times 2 to the 4th, it handles all that order operations for us, and we can just very quickly come up with our number. As long as we type in our problem correctly, it does that evaluation for us. So especially come into play with example 17, where we have a fraction we got to deal with. But let's rewrite our equation first. We are plugging in x equals 2 for this, so f of 2 equals 3 times 1/4 to the 2nd power. If you wanted to work that through, you know that 1/4 to the 2nd power is 1/16. You should get 3/16. But again, this is a fraction. It's really messy to deal with. I'm just going to rely on our good old Desmos here. We have 3 times 1/4. And I'm going to make sure I put my 1/4 in parentheses just to make sure the exponent is getting plugged in properly. And that is going to the, lost some of my notes here. Hold on. Okay, I lost a little bit of my old work, but that's all right. You should have had it down already, or you can scroll back in the video. But I was plugging this function with our 2 into Desmos, the 3 times 1/4, and that exponent is going to be the 2nd power, and that gives me 0.1875, or 3/16 is the same thing there. However you want to write that. I didn't specify how many decimals to use, so let's just write them all out here, 0.1875. When you get to your work, I'm going to ask you to round to the nearest 10th. So just make sure you're doing that appropriately in your work. And finally, example 18, x is equal to 4 again, different function though. So f of 4 equals 3 times 3. And this is to the 4 minus 1. And notice how that 4 minus 1 is all part of our exponent. So one thing that I like to do in my mind is throw parentheses around that, because we got to basically handle that entire thing first before we can take the exponent. So if we do that, we would have 3 times 3, and then 4 minus 1 is 3. So that goes to the 3rd power there. And then if you're doing that in your head or with a calculator, you'd end up with 81, because we get 3 to the 3rd is 27 times another 3. Let's not rely on that, though. Let's make sure we're using our tools that are available to us. And we can go straight from the outset here and do 4 minus 1. And again, Desmos is a little tricky about doing operations up top with our exponents. So I recommend doing the parentheses to make sure that stays up there. And we get 81 as our answer.